So let's look at a couple other vocabulary terms. In this case, we're looking at two or more liquids interacting with each other. You can't really dissolve a liquid. Dissolving is a process of dissociating and solvating. So we need a different term to look at liquids, whether liquids will mix evenly throughout each other or not. And if two liquids dissolve freely in each other, they mix freely. Those are miscible liquids. So you can think about alcohol and water. When you are 21, you can get alcohol from anywhere from 3% to 97% alcohol. And immiscible things are liquids which are not soluble in each other. So the classic example is a salad dressing, oil and vinegar. They don't mix. And whenever we get to this point in the year, I like to do my little PSA about grease fires and why you should never try to put water on a grease fire.
We never want to add water. I'm going to show you why right now. So this is 1 cup regular tap water, approximately an inch of oil in the bottom of that pan. On the count of 3, 1, 2, 3. 1, 2, 3.
Please put a lid over the pan, turn the burner off, and then leave and call 911. Do not do anything else. Do not remove the lid from the pan or try and move the pan from the stove.
And you kind of think about why this is. Water is more dense than most oil. And so when you pour the water in, it immediately sinks to the bottom of the oil level layer, but then it gets incredibly hot and starts to boil into a giant bubble of steam. Well, we know from our last unit that temperature and volume of a gas are directly proportional. So as it turns into gas and it gets really hot, that giant bubble expands, and now it's flinging tiny flaming oil particles everywhere. So as the gentleman was saying, you should always put a lid on a grease fire. That actually would make oxygen gas your limiting reactant. Once you run out of oxygen gas, the flame goes out. Alternatively, you can use baking soda to smother a flame. Same idea, it gets it away from the fuel and the oxygen. Do not use flour. Flour is extremely flammable. So a couple of other terms that you'll see, electrolytes versus non-electrolytes. If you think about Gatorade, they talk about balancing your electrolytes when you are running or sweating. All an electrolyte is a substance which dissolves in water, and that solution conducts an electric current. So if you remember from first semester, we did an experiment where we dripped solutions of sodium chloride, magnesium chloride, and aluminum chloride, and we got 3 lines as we saw the conductivity increase drop by drop. Those were electrolyte solutions. Your body needs electrolytes because your body uses ions to conduct electrical impulses down your nerves. Non-electrolytes are going to be something that does dissolve in water, but when it's dissolved in water, it does not conduct an electrical current. And so that means there are no ions here because a current is a moving charged particle. So something like sugar, which dissolves, but then does not form any ions, would be a non-electrolyte, or a miscible solution of alcohol and water would be a non-electrolyte because there aren't really any ions involved. When we do look at electrolytes, we can have strong electrolytes and weak electrolytes. Strong electrolytes are really good at conducting electricity, so those are things which are very soluble, that conduct electricity well, like hydrochloric, hydrobromic acid, sodium chloride. These completely break up into solutions, and so we get all of the ions available to conduct a current. Weak electrolytes, however, at the same concentration would not conduct as much electricity because they do not completely dissociate, like acetic acid or ammonia, which in water would form a very small amount of ammonium hydroxide. That is not the same as a non-electrolyte. A non-electrolyte does not conduct at all. There are no ions. Weak electrolytes just make a few ions, so they don't conduct as much electricity. So we're going to talk about concentration and how to measure and understand that. Concentration is an amount of solute in a given volume of solvent or solution. And you can have relatively dilute solutions. Relatively dilute solutions have a smaller amount of dissolved solute, or you can have quite concentrated solutions where we would have a large amount of dissolved solute. You can kind of think about it like if you're trying to make Kool-Aid or hot chocolate. Sometimes people like to put 2 packets of hot chocolate into one mug of water because that makes it more concentrated. You have more of the chocolate and sugar and milk in the cup, and you have a more concentrated drink. So we've actually used this unit before. What we use as chemists is called molarity, big M. Capital M is defined as moles of solute divided by the liters of solutions. That's moles over liters. Or really a lot more often for us as chemists, we use millimoles over milliliters because most of the time we aren't going to use large volumes of solution. And the nice thing about capital M molarity is if we look, we can see if big M molarity would be the same both in millimoles per milliliter and moles per liter. And that's just a matter of doing some unit conversions. If I take it in moles per liter and I want to get to millimoles per milliliter, well, the first thing I need to do is I need to convert my moles. I would put moles on the bottom here so that I can get the moles to cancel. So moles cancel moles, and I'm in millimoles. This is in millimoles per liter. I want millimoles per milliliter. So then I have to think about my opposite sides of the fraction bar. Liter on the bottom needs to be canceled by a liter on the top so that we're on opposite sides. Now I'm in millimole over milliliter. And so I have 1,000 over 1,000. So just like when we had millimoles and milligrams, the milli on the top and the milli on the bottom means that capital M molarity is the same number whether I'm using millimoles per milliliter or moles per liter. So I need to make sure that I'm consistent, that if I have millimoles, I'm using milliliters or liters and moles. So let's try a couple of practice problems. So I have 3.50 liters of solution that contains 90.0 grams of sodium chloride. What is the molarity? Okay, well, we think about what molarity is. Molarity is defined as moles over liters. So that means we're going to need to get moles. This is not grams over liters. It's moles over liters. So I'm going to take that 90 grams of sodium chloride and use the molar mass to convert that into moles. 90 grams of sodium chloride. I add up a sodium and a chloride. I get 58.44 grams per 1 mole. So now I have grams canceling grams, and I have 1.54 moles. But that's not molarity. Molarity is moles per liter. So I need a number of moles divided by a number of liters. So I'll take that number of moles, divide it by my number of liters. And if I type this into a calculator, I'm going to get 0.44, but I'm going to make sure I look at my problem and look at my number of significant digits. 90.0 is 3 sig digs, 3.50 is 3 sig digs, so that is 0.440 molar. Okay, so let's try another variation of this sort of problem. Now I have 0.8 liters of a 0.5 molar solution, and I want to think about how many moles of HCl are in this solution. So if I think about molarity again, molarity is moles over liters. So if I have moles over liters, then molarity times liters would be equal to moles. And in fact, this is a relationship that we use all the time in AP chemistry and all the time as chemists, because so much of the time we do reactions in solution so that the molecules can be moving around and able to collide and react. So molarity times volume is equal to moles. So I need my molarity, 0.5 molar, times my liters. Molarity times liters would mean I would be in moles. If I did this times a number of milliliters, I would have a number of millimoles. But in this case, with only one significant digit, it makes just as much sense to go ahead and do this in moles. So that's 0.4 moles, one significant digit to go with the one significant digit in my problem. So let's do two more quick problems and then we'll work it out. So in this one, I have 10 millimoles of acetic acid mixed with 0.250 liters of water, and it would like the molarity. Well, the issue I see here is that I have millimoles and I have liters. So I'm going to need to be consistent. I either have to work in moles per liter or millimoles per milliliter. So in this case, I am going to go ahead and use milliliters to go with my millimoles. So I would multiply this by 1,000. That moves the decimal point over 3 times. And I do notice I have 3 significant digits on both of these. So I'm not just going to put down 0.04. It's 0.0400 molar. Okay. So the last one here does a similar issue. We're going to look at this and say, I have milliliters and molarity. How am I going to get this into grams? Well, moles, or molarity is millimoles over milliliters in this case. Or I can do moles times liters equals molarity times liters equals moles. And since I want to get into grams, I'm going to go ahead and do this in moles times liters so that I'm in moles and can work in grams. And also I know once I have mole, if I multiply that by the molar mass, I'll be in grams. So I went ahead and converted this into liters so that I could get moles. If I had done 750, I would have gotten millimoles, which would be fine as long as I worked in millimoles per milligram. And I get that this is 0.0375 moles because molarity times volume is moles. And then I'm going to multiply that mole by the molar mass here, because that way mole cancels mole. And I have only 2 significant digits here because remember these are not significant. So I'm going to go ahead and round at the end to only 2 significant digits. And that would be 5.9 grams. So molarity is a really, really useful unit for chemists, especially this relationship here, where if I have a volume times a molarity, I can get a number of moles, because after all, we need to be in moles to do stoichiometry.